the topic today, growth functions. So we need to, do the abstract analysis. So we need to use some abstract notations to describe efficiencies of algorithm in a compact way. Because when you describe algorithm efficiencies, you do not want to use a lot of words. You do not want to use some complicated notations. So you want to use some relatively simple notations, but those notations can represent, some specific meanings in a concise way. All right. So let's start learning those abstract concepts. B.1, introduce growth functions. This concept. All right. Let us consider formula between running time and the number of basic operations. So here, what we are doing here, we measure efficiencies. We measure efficiencies of algorithms. When we do that, we learned before. There are two ways we used before. The first way, running time or response time, right? So after we hit the enter, start running our program, so we clock it. We look at the execution time, okay? So that running time, that's the direct measure. Straightforward, direct measure. But that measure has a problem. It's not stable. This measure not stable. So why not stable? Because the machines running this algorithm could be different, right? Some people use some low-end machines. Some people may use some super powerful machines. The result, execution time could be very different. The difference could be pretty big. So we cannot use this direct measure for a comparison. Okay. So later, we want to switch to a stable measure. So the number of basic operations. So the second one, then this one you can see it does not rely on the machines, right? So you use supercomputers, so you use some, low-end computers. You need to use the same number of basic operations. All right. Here, let us compare these two different measures. And here, we do not want to compare their difference. We want to connect them. They are closely related. These two measures are closely related. So we want that connection. We want to see that connection here. All right. First, let us use some appropriate notations for these two measures. All right. The first one, function of the running time, T of n. N is the problem size. Yeah. So we're familiar with this way, problem size concept. Okay, yeah. T, yeah. Time function. Yeah. All right. For the second one, function of the number of basic operations used, C of n. Yeah. C because we do counting. Okay, we count the number of basic operations. Yeah. So what is this concept? Here we use a concept called the basic operations. Yeah. Yeah. Its meaning is like this. The operation contributing the most to the total running time. Yes. Yeah. So if you recall the polynomial evaluation problem, we work on two types of operations, addition and multiplication. Multiplication contributes the most, right? So we treat the multiplication as the basic operation. Yeah, so that when we do the measuring, we only count the basic operations. So here you can see we ignore other relatively, or we call them minor, those roles, those operations, they play a minor role. So not a major role. Yeah. Basic operation, this one, it plays the major role. So we only look at the basic operations. Yeah. All right. Then another concept, we need to use a special notation. So that is execution time of basic operation. Little c with subscript OP. Yeah. Because each basic operation, its execution time on different machines could be different. Yeah. Supercomputer, low-end computer, this number is quite different. Yeah. Even if it is so different on different machines, but we can treat it as a constant. So it's a constant number, right? Yeah. No problem on that. So it's a constant. So that means on the particular machine, there is a constant associated with this machine. Right? So then we can use this constant all the time when we run different algorithms on this particular machine. Okay, so we do not worry about it. Yeah. All right. Yeah. So it's not like at different time you run your programs on the same machine. This constant will be different. Yeah. This constant will be the same. Yeah. All right. So with this assumption, then let us do the discussion here. All right. Formulas. Let us compare these formulas. Yeah. Here we take an approximation approach because we ignore those minor operations, right? Yeah. So that's already approximation step. Yeah. So our approximation formula is like this. T of n approximately equal C op times capital C of n. Yeah. That's straightforward approximation. Yeah. All right. So we use this approximation formula to get connection, relationship between these two functions, T of n and capital C of n. Yeah, all right. And first, we observed this property, simple property. These two functions are proportional. Yeah, because, you know, their ratio is just a constant. Little c of, that is a constant. Okay, yeah. Proportional, yeah. That means these two functions are closely related. Yeah. The connection between them is just a one constant. Okay, one positive constant. Yeah. So we can a little more accurate. It's a positive constant. Yeah. All right. All right. Yeah. And in these two functions, T of n, C of n, we will using C of n instead of T of n. Yeah. And the C of n, this function, the good thing is we just count the number directly, number of basic operations directly. Yeah. So that's most of the time, that's very convenient. Yeah. We do not need to clock anything. Hey, do the counting. Yeah. Do the counting even if we do not run our program. Yeah. We can count number of basic operations. Yeah. But for T of n, you cannot do anything without running your programs, right? You have to run your programs first. Then you can find the value of T of n function, but C of n is not. Okay. When we have the details of our algorithms, we can do the counting already. So we do not need to run our programs. So you can see which one is more convenient. Okay. Yeah. All right, but we like to explore the relationship between these two functions a little more. Okay, yeah. All right, so here the approach we take, we ignore unnecessary details. Yeah, yeah. When we do the switch from T of n to C of n, and later when we have our discussion on C of n, we need to ignore some more details. The purpose, the objective is we want to make our representation simpler, easier, but still our approximation is good enough. Here, we use approximation, right? Yeah. But we also want to make our approximation as good as possible. Okay. We don't want to have a bad approximation. We want to have a good approximation, as good as possible. All right. Yeah. So later I'll try to convince you how good is the approximation. Okay, how good is the approximation? Actually, very good. All right, yeah. But we need to ignore some unnecessary details, less important details. Yeah. The first thing we can ignore, this one. Can we ignore some constant? Can we ignore some constant? Yeah. Here, to show you some example. For example, you know, n plus 4. Here, 4 is a constant. Yeah. When we do the comparisons, when we want to look at how fast is our algorithm, can we ignore this constant? All right, so, and let's see another example. 1/2 n squared, right? This 1/2 is a constant, right? Yeah. When we want to get an idea, how fast is this algorithm? The question is, can we ignore this constant? Yeah, these two cases here we can consider. All right, yeah. Second, can we ignore some minor terms? Some minor terms. The minor terms here, if I show you one example, let's say n squared plus 2n plus 3. We refer these terms as the minor. Yeah, terms. Right? Minor terms. Yeah. Can we ignore these minor terms? Yeah. All right. Yeah. All right. First, let us take a special view. Yeah. So this view we take, we do the ratio of, for these two functions, T of n, C of n. But when we do this special ratio, we double the problem size. 2n, we double the problem size, input size, and problem size. Okay, yeah. After we double the problem size, then we take the ratio for each individual function. Okay, T of n. T of 2n over T of n, the first ratio. And C of 2n over C of n, the second ratio. Yeah. We can see if we go back to the original formula, the constant can be canceled out, right? The constant can be canceled out. So these two ratios approximately equal. Yeah. Why this view is good? This is a good view. Yeah. So we treat this as a good view. The first reason, the constant C op is gone, right? Yeah. In this formula, the constant little c op is gone. So that's good. That's a good property, because here it tells us if you look at this ratio, then the computer factor is gone. The hardware, the computer factor is gone. A fast computer, a slow computer, it doesn't matter when you consider this ratio. Yeah. But from another angle, so this ratio can tell us some useful information. How fast your algorithms increases when you double the problem size. It tells you that information. So that's kind of, some useful information to tell you how fast your measure function increases. Okay, so that information is useful. If your measure function increases very fast, grows very fast, so then that means your algorithm slower, right? Yeah, because the function value grows faster from the T side, faster, it uses more execution time, it's slower, right? From C side, you need to use more, number of basic operations. It also means slower, right? Yeah, so you can get that information easily. All right, yeah. So how fast it changes, how fast the measure function, changes when the problem size is double. Yeah. So that give us some good reason to ignore this kind of constant. This kind of constant, because when we take the ratio, it's gone. Okay, it's gone. That tells us we have a good reason to ignore this kind of constant. Okay, yeah. But how about that? Yeah, later I will explain. Yeah, so we have also good reason to ignore this kind of constant. Yeah. All right. Yeah. So let me go to the next one. Introduce the growth function concept. So with the discussion in our previous slide, now in this slide, we need to introduce a basic concept, growth function concept. Yeah. Yeah. All right. Question. What is the major term in an efficiency function? Yeah. First, when we use this concept, what do we want to do? We want to measure efficiency of our algorithm. Now, because we know efficiency of algorithm, usually we have a function expression. Okay, yeah, it is a function of the problem size. We have that function. All right, yeah. After that, yeah, we want to make our function as simple as possible. So we need to simplify it. Yeah. So we have an original expression, but usually our original expression not very simple. Yeah, it looks pretty complicated. Yeah. So it's not easy to do comparisons if the expression is very complicated. For easy comparison, so we want to simplify it. Yeah. Here, this growth function concept, we want to simplify our original efficiency function as much as possible. Yeah. All right. So let me show you. The way to simplify it, first we need to identify the major term. Okay. Yeah. The major term, we use the dominant term before, leading term, right? Yeah. I remember Sarah used that first in this class, the dominant term, leading term. Yeah. So when we look at polynomials, we have leading term, right? All right. Yeah. Recall the selection sort. Yeah. In selection sort, we sort the array, yeah, in this special way. So the efficiency function, this is the efficiency function. Okay, yeah. In this efficiency function, if we expand it, so we have two terms. The first term, 1/2 n squared term, and the second term, minus 1/2 n. And we consider the leading term, that is the dominant term. Okay, yeah. So we take that dominant term to do our first simplification. Okay, so we throw away the remaining terms. Okay, only keep that leading term. So that is the first round approximation. Okay, how good is this approximation? So later I will convince you this approximation is very good where n is large. Okay, yeah, where n is large, very large. Okay, all right. So here, dominant term, we take the dominant term from the original function. That's the first round approximation. All right. Then you can see in this dominant term, you have that 1/2 constant. 1/2 constant. Based on our previous slide, when we look at the ratio of those two functions, when the problem size is doubled, this constant is not important. It is canceled, right? Yeah. So then we do a second round approximation by ignoring this 1/2 constant again for another simplification. Yeah. All right. So we get another round simplification. Yeah. And square, and we call this one the growth function. Because that is pretty simple, and this function reflects how fast our algorithm is. Pretty good, yeah, in a good way, yeah. And it is an easy function to see how fast is your algorithm. Yeah. So that's the reason we use this growth function concept. Okay, all right, yeah. Next, I want to convince you when we ignore the minor terms, it's not a big deal. Yeah. Our approximation is still good. Yeah. After we throw away those minor terms, our approximation is still good. Now I want to convince you this point. Okay. So I like to do some calculation here. All right. Oh. Did you see? Yeah. I show a formula, but on my screen, it does not show up. I show some oh, what's wrong with it? Oh yeah. It appears after long time, 10 something seconds. Yeah. All right. Yeah. Here, what I do, I compare two terms. The first term, second term, I take the ratio. Yeah. Here, I got a message from my side that my internet connection is not very stable. Yeah. All right. And when I take the ratio, I take the limit when n goes to infinity. Yeah. Here, you need to use your knowledge, the limit, how to calculate limits in your calculus. Yeah. But this limit is very simple. Yeah. First, we do cancellation as much as we can. 1/2, the constant part cancel out, and n squared n, after cancellation, we only have n left. And when n goes to infinity, this limit also goes to infinity, right? Yeah. It tells us, if you look at the ratio, how dominant our first term is. This limit infinity tells us the dominance. How dominant the first term over the second term. Okay. Now, by convincing argument, yeah, this infinity, we know it is larger than any particular number, right? Yeah. So suppose this function give us the measure number, efficiency measure number. All right, yeah. And we look at in this measure number, we look at the, percentage of first term, second term. There is a percentage, right? Contribution percentage, first term, second term. Yeah. But where n is very large, n goes to infinity. When n becomes larger and larger, the percentage of the first term becomes larger and larger. And with the dominance, because the ratio goes to infinity, so you can see the percentage of the first term will be 99%, very close to 99%, many nines, right? Yeah. And the second term, the percentage, the second term percentage 0.00, yeah. Many zeros. Okay? Yeah. Because the ratio goes to infinity, right? Ratio goes to infinity. So you can see the contribution of the second term will be closer and closer to zero. And it could be ignored, right? Yeah. If the contribution is so little, we can comfortably ignore those minor terms, right? Yeah. So from this simple calculation, yeah, so we can see when we do that kind of approximation by throwing away minor terms, our approximation is still very good, right? So good, we just throw away this little part, right? We didn't throw away too much, right? Yeah, but under the condition n goes to infinity, that is the condition. When n goes to infinity, yeah. So here, in order to convince you completely, I need to make another argument. Thus n goes to infinity. So that is the most important thing we are looking at. Yeah, we are looking at when n goes to infinity, when n is very large, larger and larger, we worry about that part. That is our most concern on that part. Okay, so that is another argument. Here, we do not have enough knowledge to see that. Yeah. So I need to, after I give you some more concepts, then we can see that. Okay, yeah. In our part C, so we will see that when n goes to infinity. So that's the hardest part we need to worry about. When n is relatively small, we do not worry about that. Okay, so in other words, so when n is relatively small, okay, yeah, we do not worry about the measure. All right, yeah. So this point, so we will see this point in our part C. Okay, part C of this module. Okay, yeah. So our biggest concern is this part when n is very, very large. That's our biggest concern. Okay, all right, yeah. Yeah. So next, yes, compare growth functions. P.2, yeah. Here, because if recall, we go back to our part A of module 2, we have some uncompleted work, we didn't do the comparisons. We have two methods for the element uniqueness problem. Yeah, so let's recall from part A. Yeah, recall. We have two methods for the problem element uniqueness uniqueness, yeah, problem, yeah, probably this E or not, yeah. Anyway, two methods, but we didn't compare these two methods, right? Yeah, so we will do the comparison here, okay? But when we compare their growth functions. Because we just learned those growth functions. So here, for simplicity, we just compare their growth functions. Yeah. All right, so let's do that. Compare two growth functions for those two methods. Which method is better? Yeah, we want to get an idea here. Okay. For the first method, we use the worst case. CW, the first method, it corresponds to the worst case. Yeah. Worst case expression. And for the second method, yeah, also the worst case expression, n log n plus n minus 1. Yeah. These two are two original functions, not the growth function. Yeah. So we need to extract growth functions from them first. Okay. The growth function of the first method 1, just n squared. Okay. Yeah. And the growth function of the second one, n log n. Yeah. Let us compare these two functions here. Okay. Yeah. We use ratio to compare these two growth functions. Yeah. Just like what we did in the previous slide. Yeah. But here, let us consider the ratio of these two growth functions when n goes to infinity. This time. Yeah. All right. After cancellation, we find the limit when n goes to infinity, n over log n, log function, n function over the log function. Yeah. But the log function, what is the base of this log? Okay. Yeah. So here we can consider the general log base a, but this a, we like to take a greater than 1. Yeah, because only when a greater than 1, this function is positive. Otherwise, it's negative, right? It does not make sense. Yeah, so your growth function is a negative function. It does not make sense, right? Yeah, so we take, the growth function positive. Yeah. Actually, n log n, remember, this n log n comes from sort algorithm. The sort algorithm, the log, we got from there log base 2. Log base 2. So that corresponds to a greater than 1, right? Yeah. So our assumption is right. Okay. All right. And here we want to see this ratio goes to infinity when n approaches to infinity. Yeah. How do you see that? Yes. Let me show you the details. Yeah, we can see that. How do you see that? Yeah, here, let me show you the details. Yeah. The method 1, here I use two methods. Yeah. The method 1, we do some variable substitution. Yeah, because the log, we feel we cannot see log clearly. Yeah. We want to avoid that log. So we do variable substitution. We introduce a new variable called u. U equals that log function, log base a of n. Okay. Yeah, with this substitution, yeah, n equals a to the u. Yeah. Then our original limit, we switch to new variable u, it becomes a to the u over u. A is an exponential function. Okay, exponential function, we know exponential function with base a greater than 1. Yeah, still we use the base a greater than 1. Exponential function dominates any polynomial, right? Yeah, exponential function dominates the polynomial, so that should be infinity. Yeah, but to see that, yeah, to see that, we can do calculation. Yeah, we can use, calculation to see that. Okay, yeah. Later I will show you. Yeah, we can use rigorous math to see this fact, this dominance fact. Okay, yeah. Later I will show you. Yeah. All right. Yeah, here we make our conclusion based on this property. An exponential function dominates any polynomial. Yeah, so that is our, everybody knows this fact. Yeah, we can prove it. Yeah, later I can prove it. Okay, all right. That's method 1. Method 2, let's recall calculus, L'Hopital's rule. I believe many of you forgot the details of this part in calculus. Actually, it's in Calc 2. Calc 2 course, all right? Yeah, that part, yeah. Yeah, let me explain that. Yeah. Method number 2, we use L'Hopital's rule to calculate the limits here. Yeah. All right. L'Hopital's rule, when we use it, we work on limit of ratio of two functions. Yeah. But many times, if you work on directly, not very easy, pretty hard. But L'Hopital's rule tells us we can convert it to limit of the ratio of two derivatives. Yeah, that's the same. Derivatives will be easier, and then you can calculate the limit in an easier way. So that's the L'Hopital's rule. How the essence of the L'Hopital's rule. Okay, yeah, all right, yeah. But when you apply L'Hopital's rule, there are some conditions. Before you apply it, you need to check some basic conditions. So that is, the ratio should be indeterminate form, not determinate form, indeterminate form. So what's the indeterminate form? Infinity over infinity. So that is the first indeterminate form, because that cannot be determinate, right? Yeah, it could be anything, infinity. So that's the form. Yeah, do not treat as we use that real infinity over real infinity. Do not treat that. Okay. Yeah. So here we look at that as a form, as a form, not as a number. Okay. Yeah. If you treat this expression as a number, It does not make sense. It does not exist. There is no such number that equals infinity over infinity. Okay, so we do not treat it as a number. We treat it as a form. Okay, so that the meaning of that form, it is the ratio of two functions. The numerator function approaches to infinity when n is where n goes to infinity. The denominator function also approaches to infinity when n goes to infinity. That's the meaning of this indeterminate form. Okay, all right. Another possibility is 0 over 0. All right. Still, we treat it as a form, not a number. If you try to understand using the number way, 0 over 0, it does not make sense. Okay, yeah, it does not exist. There is no such number. Okay, but if we understand it as a form, it makes sense. As a form, it makes sense. Okay, so that means the numerator function approaches to 0 when n approaches to certain number. Similarly, for the denominator function. Okay, yeah, all right. Here, let us consider, yeah, so now I show you how to calculate that a to the u over u. This is an indeterminate form. Yeah, I use L'Hopital's rule to show you. This one, okay, yeah, it corresponds to infinity over infinity indeterminate form, right? So, yes, after you identify it is an indeterminate form, then we can apply L'Hopital's rule correctly. Otherwise, some students forget to check the indeterminate form. Then, if they still apply L'Hopital's rule, they may get a wrong answer. Okay, wrong answer. Yeah. All right, so now we apply L'Hopital's rule. Let's take the derivative. Yeah. By the derivative formula, the derivative of an exponential function, it equals natural log of a. The base number, we take a natural log as the constant, then multiply this exponential function again, a to the u again, and denominator u, its derivative is 1. Its derivative is 1. Okay, yeah, by the power law, right? Power rule. Okay, so u to the n derivative, there is a power rule. Because this is a power function. Okay, power rule, its derivative is n times yeah, n times u to the n minus 1. Okay, yeah. Yeah. Here, so by that power rule, derivative is 1. Okay, yeah. Then we can see when u goes to infinity, yeah, here, this new ratio, you should not take L'Hopital's rule another time because it's not an indeterminate form. Yeah, the numerator is 1, constant. It does not go to infinity. All right. Yeah, the numerator is a constant. Yeah, so you should not apply L'Hopital's rule. Second time, you will get a wrong answer. All right. Yeah. So we just, because here we ignore the constant part. Yeah, the ratio 1 is gone. The constant part never changes. So where u goes to infinity, that exponential function goes to infinity. Yeah. So that is the answer we used in the previous slide. Okay. Yeah. So here we do the rigorous math. We can see that. Okay. Yes. All right. But in this simple example, we use that L'Hopital's rule. All right. Calculus. Calc 2. All right. Yeah. Okay. Yeah. Yeah. Definitely we need a greater than 1. Otherwise, yeah, think about if a, yeah, if 0 less than a less than 1, we won't get this infinity. So we will not get that infinity answer. Okay, yeah. So the range for a is also important. A greater than 1, strictly greater than 1. Even 1, it's not good. We have to exclude one case. Yeah. All right. Yeah. Even 1, we cannot. Yeah. All right. Yeah. All right. Yeah. Yes. But here, yeah, there is another issue I may need to, because I mentioned the rigorous math, right? I mentioned that rigorous math. Yeah. Here for the rigorous math, when we apply L'Hopital's rule, we need a continuous variable. Continuous variable. What do you mean continuous variable? Okay. Your variable can take values of all real numbers. Yeah. Your variable can choose numbers that can change continuously. Okay. Yeah. Not discrete variable. Not discrete variable. All right. So how to get that point? Yeah, here. This is another here regarding the rigorous math. Okay, regarding the rigorous math. All right. So let me make this point here. Yeah. Why we need to use the continuous variable here. Yeah. All right. Let's look at this limit. Limit of the ratio n over log m when n goes to infinity. Yeah. First, let's look at the values for n. Because we know the meaning of n, the problem size, right? Its original meaning, problem size. And the valid numbers for the problem size, natural numbers, right? 1, 2, 3, and so on. Natural numbers, not arbitrary numbers, right? 1.2, that's not a good problem. It's not a valid problem size. 8.5, that's not the valid problem size number. Right? So here, the two functions, n and the log n, we use the discrete variables here. Discrete. Okay. Discrete variable here. All right. Yeah. Discrete variable here. The discrete variable, then we cannot take derivatives. Derivatives. Yeah. So here, derivatives require continuous variables. Okay, continuous variables. Yeah. But how to get around that? Yeah. If you do not do anything, you just apply L'Hopital's rule on this discrete version of the ratio function. Your work is not rigorous. Okay, your work is not rigorous. Yeah, so we should avoid that. Yeah, because we may get trouble if you do not do your work rigorously. Sooner or later, you may get trouble. You may get some wrong conclusions. So we want to avoid that part. Okay, so we are doing science. It must be rigorous. Our logical reasoning must be rigorous. All right, yeah. Here, but we can get around it. We can solve that problem easily. Okay, all right. So the logic is like this. All right, yeah, discrete variable. All right, the logic is we convert discrete variable to continuous variable first before we do the calculation. Before we apply the L'Hopital's rule, we do conversion from discrete variable to continuous variable. All right, yeah. So how to do that? We consider the continuous version of the ratio. How about that? We consider, now we replace discrete variable n by a continuous variable x over log function of x. But this time, our x, we can take 1.2, 8.5, and so on, right? We can take any positive real number. Yeah. So because our n is not necessarily the same as n, right? So any positive real number is allowed here. Okay. Yeah. There we have no problem to apply the L'Hopital's rule, right? Yeah. Yeah. All right. So we can take the derivative. The derivative of x equals 1. Okay. The derivative of that log function, we assume the log base is a. Yeah. So that is 1 over bracket natural log of a times x. The derivative formula for the log function. Okay, yeah. After simplification, we take the limit when n approaches infinity. This limit function, natural log of a, the constant, times variable x, when n goes to infinity. It is infinity. Okay, yeah. But this limit, we use the continuous variable. Yeah, goes to infinity. All right. But our original limit, that's on the discrete variable. So the question is, can we come back after we get a conclusion for the continuous variable version of the ratio of the limit? For the limit, can we come back to the discrete version to make a conclusion? The question is yes. Yeah. So we can come back to our discrete variable version and make the conclusion. Its limit is also infinity. Why this kind of conclusion is correct? Yeah, the reason is very simple. The reason, yeah, to explain that, we go back to the definition of limit. Let's recall the definition of limit. Yeah, how do we define limit of a function in our calculus? Yeah. Here, I do not need to show you the complete definition here. Here, I just explain, yeah, the basic idea when we define the limit of a function. Yeah, so here, limit of a function when n approaches to infinity. Do we need to take any specific way for x to go to infinity? Yeah. How does x approach to infinity? So here's the question. How does x approach to infinity? Because there are so many different ways to approach for x to approach to infinity, right? Yeah, so many different ways. Yeah, for example, so here for x approaching to infinity. Yeah, here I can take two different ways. The first way, 1, 2, 3, and to infinity. Second, 1 square, 2 square, 3 square, it's another way, n square way to infinity. We have infinitely many different ways to go to infinity, right? Yeah, you can also, use log 1, log 2, log 3. That's also log of n to infinity, right? There are so many different ways to approach to infinity. Yeah, but in our limit definition, do we need to specify which way for x to approach to infinity? No, we do not need to specify. No need to specify any way. So any way works, okay? The limit, any way to infinity works. Okay, yeah, that's important. So that's from the definition of the, yeah. No matter which way you take for x to approach to infinity, the answer is correct. So that's the limit definition. All right. Yeah, here we just use that because any way works. Let's take the discrete way. How about that? Yeah, here we take the way, one special way, the discrete. Yeah, so or let's say, yeah, because discrete could be any discrete values, right? Yeah, so here let's take the natural number way. Natural number way. Okay, yeah, we take the natural number way. All right, yeah. After we did a calculation for the continuous variable to get the limit, then we take the special natural number way. It's still correct. Okay, it's still correct. Yeah. So in this way, we get around the discrete variable problem. We get around it. Okay, yeah. And our logical reasoning is completely rigorous here. Okay, no problem, completely rigorous. All right, yeah. And here, I spent a lot of time to explain that because this non-rigorous way is in our textbook. Okay, in our textbook, it used this non-rigorous way. So I want to point it out, okay? Yeah, so even if it appears in our textbook, but it's not rigorous, all right? Yeah, you should avoid it. You should avoid this kind of logical reasoning, non-rigorous logical reasoning, all right? All right, yeah, so I run out of time. Yeah, so let me stop right here for our part B of module 2.